The Earth has been a living planet for nearly 4 billion years. In that time, nature has had to solve all the varied problems of life. Finding food, finding mates, moving around, and surviving in extremes. From the highest of mountaintops to the freezing ocean waters. In the beginning, people were just another part of this breathtaking diversity. But our large brains began to set us apart from the natural world as we used technology to solve the problems of life. That alienation made us extremely successful, but at great cost to our planet. Now we're beginning to see nature with new eyes. At the start of the third millennium, we stand on the brink of a new revolution, one where nature and technology stand hand in hand. The new science of biomimetics looks to nature for inspiration and is finding answers to our modern problems in totally unexpected ways. From how to move around, to new materials, and new ways of building them, and even how to solve the energy crisis. The answers are already out there, in nature. All we need is for nature and technology to work together. Nature has solved the problem of moving around in some wonderful ways. Legs, wings, and fins have all been invented by evolution many times. But all these creatures have one thing in common. They have to travel as economically as possible. Nature abhors waste. No creature that wastes energy will survive the unforgiving hand of natural selection. So we must be able to improve our own technology by looking at walking, swimming, and flying. But can scientists really learn anything new from nature? After all, we've come up with incredibly successful ways to travel around our planet. We can move faster than anything in nature. We can find our way with unerring accuracy. We can even build flying machines much bigger than anything nature could ever dream of. The biggest thing nature can get into the air is this swan. But it was birds that first gave humans the idea of flying. Dreaming of flight and actually taking to the air are two very different things. And despite imaginative ideas like those of Leonardo da Vinci, people would remain firmly earthbound for centuries. Then, around 100 years ago, the dream finally took off. Pioneers like German engineer Otto Lilienthal began to find ways of getting off the ground. Like Leonardo, he made detailed studies of birds. He reasoned that the shape and structure of the wings was vital to the bird's ability to fly, so he modeled his designs along similar principles. This was the right approach, though it would be many more years before anyone understood why his designs worked. The shape of birds' wings creates a spinning mass of air, a vortex, around the wing. When the bird is moving forward, this circulation causes the air above the wing to move faster than the air below. The faster air moves, the lower its pressure. So this means that the air below the wing is at a higher pressure than the air above, creating an upward force. Lift. The key to taking to the air. Of course, birds are much more complicated than that. They also flap their wings to produce forward thrust. A bird's wing is both wing and engine. Lilienthal's real bio-inspired breakthrough was to separate the problems of lift and thrust. He thought the only way to conquer the air was first to master gliding, which he did with incredible success. In all, he made 2,000 flights. His pioneering flights laid the foundations for the next stage in aviation, a step taken in America by the Wright brothers. These two bicycle makers from Ohio made the first ever powered flight. But this first Wright flyer was almost impossible to control. This historic moment wasn't exactly a display of precision flying. The Wright brothers still had to work out how to steer their plane, a problem nature solved a long time ago. The goshawk has perfected the art of aerobatics. It hunts its prey through dense forests, so needs to twist and turn at high speed. It's impossible to appreciate its performance in the wild, but slowed down 100 times, its aerial skill is breathtaking. And birds also gave the Wright brothers their breakthrough. They didn't have the technology to look at how a goshawk maneuvered in flight. But all they had to do to find inspiration was to look up. Turkey vultures were a common sight around their home in Ohio. And these birds fly with a slow, lazy, gliding flight as they circle over the ground searching for carrion. It's much easier to see with the naked eye how they control their flight path. They seem to steer by twisting their wings, and the Wright brothers took this idea and applied it to their later planes. It worked so well that the Wright brothers were able to join the vultures, soaring over the prairies for hours at a time. So aviation may have only got off the ground through inspiration from nature. But over the next century, aviation engineers went their own way and ignored nature's designs. But many of our cleverest engineering solutions have exact counterparts in nature. For birds and planes, the hardest part of flying is landing or taking off. When a wing is moving slowly through the air, there's much less lift, making it harder to stay in the air. The engineering solution is to make the wing bigger by extending flaps at the rear. And nature does the same. A hunting barn owl flies slowly, listening for the slightest noise in the grass that might reveal the location of a mouse. In slow flight, its feathers are spread out to give it maximum lift. A bird can change the shape of its wing far more dramatically than a plane, giving the barn owl its ability to hang in the air until it pinpoints its target. These striking parallels between nature and technology meant that, during the whole century of aviation, engineers spent a lot of time reinventing the wheel, or at least the wing. Now, with the birth of this new way of thinking, of bio-inspired thinking, engineers are looking to nature when designing the next generation of aircraft. These robo-gulls at Florida State University are radio-controlled models, with wings that behave more like those of birds. These planes can change the way they fly, just like birds, making them much more adaptable than conventional planes. This one changes the area of its wings, in the same way as a bird does, by sliding its feathers apart. Birds can also alter the angle of their wrist joints to change their flight characteristics. And so can this plane. With its wings in the wrist-down position, the plane is less stable but very maneuverable. With its wings straight, the plane glides well, and with the wrists up, it's more controllable and easy to land. This plane is steered by wing warping, a system abandoned by engineers shortly after the Wright brothers, because, although very efficient, it needs constant adjustments and instantaneous reactions. All these planes fly, but because they behave like birds, they're very difficult to control. Evolution has turned the bird's brain into an ultra-fast control system, an onboard computer capable of making continuous, lightning-fast adjustments to wing shape and angle. Just how fast a goshawk's reactions need to be can only be seen when its dash through the trees is filmed from an onboard camera. The researchers from Florida State University really appreciated the goshawk's instinctive skill when they tried flying their robogulls by remote control. It took a lot of practice to keep these things in the air. But once mastered, these little planes are highly maneuverable. Meanwhile, at the Technical University of Berlin, scientists are using a specially designed wind tunnel to study a different aspect of bird flight. Attached to the front of this wind tunnel is another innovative design by natural selection, a stork's wing. The long, finger-like primary feathers are spread and turned upwards in flight. This reduces the amount of drag, which would otherwise slow the bird down. For birds like storks and vultures, A wing with low drag is critical. It gives them a much better performance as gliders. We've invented a similar trick. Upturned winglets on the end of the wings of modern aircraft serve the same purpose, reducing drag created by vortices spinning off the wing tips. But nature's system is more adaptable. It's automatic. As the airflow increases over the wing, the primaries bend up into just the right position, and multiple winglets are more effective. Using a series of models of a stork's wing, the scientists here worked out the best arrangement of multiple winglets. Then they went a step further than nature. They took away the individual feathers, just leaving a loop at the end of the wing. By extending this idea even further, the scientists made this model, where the whole wing is a loop, allowing the plane to fly at walking speed. The real joy of bio-inspired thinking is not always in the obvious, but in the leap to new and unexpected ideas. By understanding the way a stork's primaries work, these scientists have designed a way to make more efficient wind turbines. Based on the design of the stork's wing feathers, they arranged vanes in a circle. As they shed their vortices into the center, the vanes increase the airflow here. So when a windmill is pulled back into the center of this structure, it picks up speed. Inspiration for new ideas can come from anywhere. There are more than enough ideas just around the house and garden to keep a scientist busy for a whole career. Take the humble fly, for example. It might hold the secrets to new kinds of spy vehicles or search and rescue equipment. To most of us, it's just a germ-carrying nuisance. But look again. It can do things no engineer can. Until a few years ago, scientists had no idea how flies flew, let alone how to copy them. But now the fly's secrets are being unraveled, and it needed a whole new branch of aerodynamics to understand it. Deep in the basement of Caltech, the California Institute of Technology, there's a fruit fly with a half-meter wingspan, a working model, submerged in hundreds of liters of oil. The oil behaves like air would over the tiny real fly. Injecting air bubbles into the oil shows the scientists what happens as the insect flaps its wings. An exact replica of the real thing, but at a scale which makes it easier to study. The wing creates spinning masses of air around it. Some of these vortices spin off beneath the wing, producing some lift. But the scientists noticed that one vortex stays attached, just behind the front edge of the wing. And it turns out that this leading-edge vortex is vitally important in allowing the fly to fly. This is what generates most of the lift. Understanding how insects fly should mean we can build smaller and smaller flying machines. But so far, machines like Delphi at the University of Delft in the Netherlands is about as small as we can get. Delphi doesn't, at first sight, look like any insect that ever lived. Its two pairs of wings are stacked one on top of the other, not one in front of the other like an insect. But the inspiration behind Delphi came from watching the aerial skills of dragonflies. And it uses the same tricks as insects to fly. Most of its lift comes from a leading-edge vortex that forms over its wings, just as in a real insect. Flapping flight was abandoned by aviators before it ever got off the ground. But now, understanding how insects fly, we can build flapping flyers that really fly. And not just fly. In flight, Delphi looks very much like a giant dragonfly. And like the real thing, it can hover. Delphi also carries a tiny onboard camera, and its slow, maneuverable flight would make it the perfect reconnaissance machine for confined spaces. Though it's still not as good as the real thing. But as a designer, nature does have one big disadvantage over humans. It can't start from the drawing board each time. It has to work with what it's got. The ancestors of penguins flew through the air, whilst today they fly through water. Nature had to take a design adapted for one thing and make it do something else. That penguins can move through the water so easily shows just how effective natural selection is. So penguins might be the obvious creatures to study for designing better ships and submarines. Perhaps. But at its best, biomimetics is never that obvious. When it comes to underwater energy efficiency, it's much better to take a close look at sharks. They seem to use far less energy than they should. And to find out why means taking a very close look. Magnified hundreds of times, shark skin is covered in tiny scales, each with a ridge along its center. These ridges trap a layer of water close to the skin, which reduces friction as the shark moves through the ocean. One swimsuit manufacturer has now made suits covered in minute shark skin-like ridges. Then they analyzed the shape of a swimmer's body and, just as the shark does, only placed ridges where they're most effective. This should, in theory, reduce drag by around 4%. Well, that's not much, but in competition against the best in the world, it might just be enough. At the 2004 Olympics in Athens, Australian swimmers wore these new suits for the first time and kept ahead of the field. Whether it was the shark skin effect or good old-fashioned better training is hard to say. But they might just owe this gold medal to one of the ocean's most efficient predators. At first sight, the dumpy little boxfish looks to be the complete opposite of the sleek, streamlined shark. But it attracted the attention of car designers at Daimler Chrysler in Germany. When they studied it more closely in wind tunnels and computer simulations, they found that it was very effectively streamlined. And because, like a car, it's shaped like a box, they modeled a car based on the boxfish. When they tested their new boxfish car in a wind tunnel, they found it had 65% less drag than the average family car. But as efficient as nature is, it's never come up with one innovation that we have: the wheel. Wheels are very energy-efficient ways to move around. But the problem with wheels is that as the ground gets rougher and rougher, wheels get less and less effective. Nature's solution, on the other hand, has no such problems. Legs. And what insects can do with 6 of them is truly remarkable. For one thing, the whole system operates on minimal computational power. An insect's brain just tells it when to stop or start and perhaps how fast to walk. But all the complex coordination is done by simpler control units in the legs themselves, a system which turns out to be incredibly adaptable. With just a small change in its control system, this stick insect switches from walking to searching for a new foothold, and then crossing a gap that would stop most robots in their tracks. So at Bielefeld University in Germany, stick insects are put through their paces to see how this system works. Researchers here have found that the stick insect has separate controllers, not just for each leg, but for each joint of its legs. These work with sensors in the legs which fine-tune what amounts to an automated walking system. Exactly what some robot designers are trying to achieve. Tari 2 was built to mimic a stick insect. Each individual leg control unit can be programmed in different ways to test assumptions about how stick insects walk. The more Tari 2 walks like a stick insect, the closer these scientists are to understanding how the real insect walks. Information which could then be used to make walking robots with insect-like economy. But insects can do more than just walk. They can run at very high speed. This roach can cover 50 body lengths in a second, which is why we only ever catch a glimpse of them. But slowed down more than 100 times, this unloved pest becomes a source of inspiration. At the University of California in Berkeley, scientists are looking at just how fast different kinds of cockroaches can run. As this death's head roach runs, it turns an air-cushioned ball, allowing a computer to measure its performance. And persuading it to run on a treadmill, the scientists can film it in ultra-slow motion to see in detail how its legs work. The legs act like miniature pistons, ramming into the ground. And the scientists found that the roach's legs are not stiff like a robot's legs. A certain amount of give seems to make a running roach more stable. Likewise, their sprawling gait seems to be another reason why we don't often see roaches fall over, even when running at high speed. Putting these insights together, scientists at Stanford University in California came up with Sprawlita. Its legs are pistons that mimic the way a roach's legs push against the ground. And its legs both give and sprawl like a real roach. And this cockroach-inspired design does give it a reasonable turn of speed. This robot can cover 3 body lengths a second. This prototype is programmed and driven by a large control unit attached by cables to the robot. But, inspired by the success of the basic design and by the control systems of insects, Sprawlita evolved into iSprawl, a remote-control version. And with a few further improvements in leg design, iSprawl can cover 15 body lengths a second in a surprisingly roach-like manner, though not yet close to the fastest roaches. But roaches aren't the only creatures providing inspiration for robot designers. If anything, ghost crabs are even more impressive performers. They can also run at speed, but on 8 legs, not 6. And they can switch from running forwards to sideways to backwards without ever breaking stride. Back in the lab, the ghost crab's running skills can be studied in more detail. They're also the perfect all-terrain vehicles. In this experiment, air bubbled through the sand turns it into the equivalent of quicksand. It slows the crab down. But a change in its gait, the crab's version of low gear ratio 4-wheel drive, means it can easily cross this obstacle. And back on the treadmill, the scientists can also measure how much energy the crabs are using to move. And some very unexpected results are beginning to emerge. As they measured more and more species with different numbers of legs, they found similar relationships between the energy used and the forces that these creatures generate when walking, between animals as different as humans, crabs, and dogs. 1 human leg is the same as 2 dog legs, or 3 roach legs, or 4 crab legs. An underlying principle of walking seems to be emerging, and this holds all the way up to a millipede with 180 legs. Understanding the basic principles behind nature's designs is the key to successful bio-inspired thinking, and millipedes, crabs, and roaches seem to be leading to totally new robot designs. Nature's walking machines rarely break down, and that's because nature goes in for a lot of redundancy. There's always a backup system. Creatures like millipedes and centipedes dramatically illustrate this principle. They have multiple repeated segments, each doing the same thing. A great many of these segments would have to be damaged to stop this 10-centimeter giant centipede from moving at speed over the forest floor, and its long, thin body allows it to squeeze through narrow gaps in pursuit of prey. At Penn State University in Philadelphia, this segmented robot works on just that principle. When it wants to move quickly, it can roll into a wheel, but then it unfurls to move like a mechanical caterpillar through narrow gaps. And it will take the loss of several of its segments to bring it to a halt. Giving a robot segments means it can behave even more like a centipede, making use of serpentine movements to move at high speed. The wheels on this robot are not powered. They merely allow the robot to glide over the floor, driven by its centipede-like undulations. But it's also possible to have the best of both worlds, of technology and nature, by combining wheels and legs. These robots do just that, hence their name, WEGs. This is, in essence, a cockroach on wheels. Wheeled legs give these robots the advantage of wheels, but with the roach's ability to negotiate obstacles. But roaches are still much better at covering rough ground, even at top speed. It only takes a slight change to their control system to allow them to do this, something that attracts as much envy as admiration from robot designers. And something else roaches do without breaking stride is climb up vertical surfaces. They do this by using tiny claws on their feet, which hook into any irregularities on the surface. How they attach and release these hooks is the secret to their success, a secret that has been unraveled by scientists at Stanford University. They've produced SpinyBot, a robot that can climb vertical surfaces using cockroach-like claws and an ingenious mechanism for hooking into the tiniest of cracks. But some insects can go where even roaches fear to tread. Flies have little trouble in climbing up smooth surfaces like glass, where a roach's claws would have nothing to hook into. A trick that's down to the fine details of the fly's foot. Magnified more than 1,000 times, a fly's foot is covered in huge numbers of tiny hairs, each of which ends in a flattened plate. The fly oozes an oily liquid into the hairs, which sticks each of those thousands of plates onto the glass by a process called liquid adhesion. The same thing that causes a beer mat to stick to a wet glass. Robot designers have looked at flies, but concluded that robots that leave oily footprints wouldn't be a good idea, especially when there are bigger creatures that can climb smooth surfaces that might be easier to mimic, like tree frogs. The frog's feet are covered in mucus, but they don't seem to work in quite the same way that a fly's foot does. Because the frog is so much bigger, the mucus on its toes would have to be thicker to stick it to the glass, and then it couldn't unstick its feet. After all, climbing is as much about letting go as hanging on. When scientists looked closely at this mucus, they were surprised to find that it's not much thicker than water. Easy for the frog to lift its feet, but not sticky enough for it to hang on. The answer to this mystery lies in the fine detail of the frog's toes, a precise pattern of hexagonal plates. Each plate can move separately to line up with any irregularities on the surface, and the canals carry away any excess mucus that might separate the plates from the surface. At smaller scales again, each plate is covered with tiny bumps, the tips of which make close contact with the surface. So close that it's friction that stops a frog sliding down the glass, which is making car tire manufacturers sit up and take notice. Perhaps new and safer tires based on the toes of a frog? But for sheer sticking power, nothing beats this creature, a gecko. Geckos can race up a vertical wall with no problems. And they can even hang upside down from the ceiling. It's been calculated that a gecko's feet are so sticky that it could support a weight of 25 kilograms before it falls off. All this on dry toes with no kind of adhesive whatsoever. Again, the secret lies in the microscopic detail of the gecko's toes. Like the fly's foot, the gecko's toes are covered in a dense mat of hairs. Moving closer still, each hair branches at the tip into dozens of microscopic hairs, each of which is so tiny that it can get incredibly close to the surface of the wall. So close that it can feel the forces that attract molecules together, the van der Waals forces. The molecules of the gecko's hairs and those of the wall are drawn to each other. And the force, magnified millions of times by the huge number of hairs, produces the incredible stickiness of the gecko's toes. But with such sticking power, unsticking is a real problem. The gecko has to curl its toes to unpeel them from the surface before it can lift its foot. Scientists have developed a sticky tape covered in microscopic pillars that works on the same principle as a gecko's foot. But before they can use it to build their own mechanical geckos, they have to work out a way of unpeeling it, so the robot isn't just stuck in one place. At Case Western Reserve University in Ohio, this little robot has been designed to study just that, the way gecko tape sticks to glass and then unpeels. Once perfected, it should allow much bigger robots to climb as securely as a gecko. Whether climbing, walking, or flying, robots need a way to move their limbs. Often, designers use some sort of motor, where nature uses muscles. But these robots have been designed with devices that mimic the action of muscles. Flexible tubes in the same position as muscles are driven by air pressure, which forces the limbs to bend or straighten. A very similar action to living muscles, and the result is most lifelike. In most animals looked at so far, the energy needed to walk varies in a predictable way with the size of the animal. But nature has come up with one or two surprises. When caribou walk, they use far less energy than predicted by our equations. And when they move from hard ground to soft snow, the energy they use hardly increases. It's not entirely clear how they perform this trick, though their hooves certainly play a part. They're only loosely attached by ligaments, and so can splay out like snowshoes when pressed onto the ground. But the real secret of their success must lie in making each swing of their legs as economic as possible. The caribou's extreme energy efficiency has been shaped by their need to make long treks over snowy landscapes. Each year, they move from more sheltered areas in the south, where they spent the winter, to more exposed coastal slopes, where the females will give birth. Here, the grazing is better, and they should find some respite from uncountable swarms of biting insects. But no one's yet braving these remote, mosquito-infested regions to work on a robo-caribou. Especially when there's more than enough inspiration much closer to home. Our own bodies have also been shaped by natural selection to produce our unique two-legged gait. Engineers at Honda in Japan have made detailed studies of the human leg as they've evolved their own bipedal robot, Asimo. The positioning and flexibility of the joints in Asimov's legs have been carefully modelled on those of humans, giving Asimov a very human-like movement. But walking on 2 legs, rather than 4 or 6, is inherently unstable. We've solved this problem by having sophisticated balance organs in our ears which, working with sensors that tell us the position and angle of our joints, produce some truly remarkable results. Asimov's designers have copied this system and given it a range of joint and limb sensors, which means Asimov can walk, run, turn, and even climb stairs extremely well. Asimov uses a lot of energy to achieve its amazing performance, but it's possible to make a bipedal robot with the energy-efficient leg swing of a caribou. This robot has no power supply and no sophisticated control systems, but it can walk down a slope and coordinates its legs to avoid falling over. Give it a power supply and you've got Denise. All that this robot has is a sensor on the bottom of each foot. When one foot hits the ground, that tells the other one to kick off. Most of the energy to move forward comes from the pendulum-like swinging of the leg, just like a caribou. Denise uses only about 1/10 of the power of Asimov, and she's an empty-headed robot. All her coordination takes place without a central computer. In some ways, more like an insect. Asimov is the exact opposite. All its complex abilities are controlled by a wireless link from a powerful computer. This is a very different approach from those studying the simple, localized controllers of insects. Asimov needs a complicated central controller. There's a model for this in nature: the human brain. But no one has yet come close to really understanding how that does what it does. As a new way of seeing the world, bio-inspiration is full of promise for new technology. But it's also a new way of seeing nature and of appreciating the vast complexity of life. But the real joy of this new view is that inspiration can come from anywhere, from the lowliest creatures that we might just swat to our own bodies. Nature is the biggest research library on the planet. It's just a question of knowing how to read it. In the next program, we see how, using nature's designs, we can manufacture advanced, intelligent materials and develop elegant and unexpected methods of building.